Thank you everybody for coming to join us and inviting us to speak today. Yes, we're going to be talking about our Sim for CamSense project. If you want to look at an ambitious project that is all about collaboration and is going around how to deal with common policy, then these are the framework of what we've been working around. So it's been a fantastic setup. And also previous presentation talking about what to test, how to test, and when to stop. We're taking that a step further and saying, when you are deciding to use simulation, how good is it? And when can we keep improving that? And when can we ensure that people really do trust in that simulation? So very quickly, who are we, or who am I? I'm Matt Daley, I'm the Technical Director of RF Pro. We are a simulation company, and we produce the world's leading simulation software, as well as digital content models. That means locations, vehicles, pedestrians, things that fill those digital worlds. And our core mission is really to try and help reduce the reliance on real-world testing. And that's not just in the autonomous space, that's in the automotive space and also in the motorsport space as well. So I'm here to talk about the Sim for CamSense project, as we said. That's funded by Innovate UK and the CCAV. Or it's an Innovate UK project funded by CCAV, if I've got that the right way around. And we have taken the whole vision that there should be mobility for all. And that's because it needs to be more efficient, lower operating costs, and safer for people. And in order to ensure that those AVs are safe to deploy, we need to satisfy the regulators that those vehicles have been developed well. And we believe simulation is essential if AVs are going to be developed and those safety assurance cases are going to be signed off. But there are absolutely massive challenges that we have when we're trying to bring people into the full confidence in simulation. And that's because these vehicles have a huge array of different sensor types, which are dealing with different physics and different parts of the electromagnetic spectrum. There are many then different effects, and we've just heard before, the different weather effects, the different locations that start to affect the sensor performance. And then there's just a huge, vast array of data and of different training data that you need to put into these things. And we need to prove it's credible. I'm standing here with the absolute belief that we can have simulation data and synthetic data forming the core part of the way we develop these vehicles and test that they're safe in the future. And we've got to prove that to the industry as well and to the regulators. So our big challenges, as we've said, we've taken on as a collaboration to look at three main things. How do we quantify and simulate the perception sensors under all conditions? So again, if you're looking for an ambitious task, this is not saying I can do hundreds of thousands of dots going along lines and saying, was I making the right decision? This is really going to some of the core safety critical things on vehicles, and that's how they are perceiving the world, which is such a difficult problem. And then we're saying, how do we generate that vast array of data to use for machine learning? And how do we pull together this framework, this idea of proving as best as we can that this simulation is going to give you credible answers to take forward? So collaboration seems to be the theme of this morning, and we've pulled together a really powerful group of companies and organisations here in the UK. And we've done that with sort of four main areas of interest. Firstly, around the sort of systems engineering level. What is it we're trying to achieve and these systems are trying to achieve? Then the sensor developers, and what are those sensors that are then being used to achieve that system level performance? Some world-leading organisations in measurement and characterisation of how we actually are going to test those sensors. And then bringing for ourselves and our partners, Claytex is actually the leading partner on this project, and we support them in all of their activities in this. And we're there to provide those virtual models, both from our side on the virtual world and the camera side, and with our partners at Claytex, how do we build high-fidelity LiDAR, radar, ultrasonic models as well to go into these products. And we've structured the project in four main areas of work. Alan is here from CCAV, who's leading Work Package 1. And that's really looking at quite a high level and saying, what are the systems, what sensors are on those systems, where are they working, and therefore how can we define the specifications that those sensors, that the sort of the ODD, but also the performance specifications that those sensors should be meeting. When you understand that, you then know where to go and test and collect your data with those sensors. So there's a huge range of different test facilities that have been used to collect data in lots of different conditions. And then we come into the third work package, which is the one we're mostly involved in, which is then how are we simulating and trying to match this real-world data collection with our simulated tests. And alongside that then, working with Oxford RF and looking at how do we bring forward some of the most novel sensors that are coming into the industry that are going to change the way that people are architecting vehicles, and how can we from the beginning learn how to model those and pull together the whole safety case that goes around the deployment of those into AVs of the future. So very briefly, as we say, that first area of thinking about systems, there's work on how to characterize the CAV catalog, how to build up a very useful industry resource in what are all of the different types of vehicles that are being used for autonomous driving, classify them into different groups, build up generic data sets about them. Are they passenger shuttles? Are they robo-taxis, highway freight? Because each of those has a different ODD and therefore a different set of sensors in different configurations. And some of them are working at low speed, short range. Some of those are high speed and have very far range and different weather conditions they have to deal with. So this whole part of the project is about understanding the different requirements so that we know how to go and test the sensors that are being used on those different vehicles, looking at very specific characteristics that are the most safety critical for each of those applications. Then the second work package is all about the data collection. So first of all, people like WMG are with us, looking at what's the state of the art. How should we be thinking about noise factors for our sensors? And what are the different material properties that we might have to understand about objects that these sensors are looking at? Then we're doing measurements. Those measurements are both lab-based as well as external, so that we can get very controlled conditions about materials. And then some great work looking at how do sensors perform in a huge range of different weather conditions over a long period of time. Then we go about the modeling part. So obviously the first thing we have to do is recreate those physical conditions and those physical tests in our simulation. We have to create the sensors that we've used. And we will come to, not there yet, but comparing those results. And that's the big challenge now for the rest of our project is how can we try and identify where we're strong in the simulation and where are our opportunities to improve and really hone in on the safety critical aspects of those sensors. Ourselves then, we're trying to improve the core simulation, which isn't just about the sensors. It's really thinking about the world and the weather outside. So we've been adding physics-based volumetric fog models, thinking about how light and all of the different sensors are propagating their energy through the world, and how that is then reflecting off the surfaces and coming back into models of the electronics of those sensors as well. And the key area we keep coming back to is we need to prove this. We need to be building our own sort of safety case of our software as such. So there's a lot of constant work trying to understand what are the common policies that exist. Is it the BSI? Is it ISO standards? Is it the UN type approval? Is it the new UN ECE project that's constantly ongoing? I mean, it's great that there's obviously a desire in the industry to start to define, as far as we can, how we're going to sign these things off. It's just a shame at the minute that we keep having to look at 4 different ways people are trying to do this. But overall, what we're trying to create is that simulation handbook, the physics-based approaches to our methodologies that people will be able to put their hand on later and say, yes, that 85% of testing you did in simulation, we believe, just as much as we believe the 15% that you've done in physical testing. As we say, the fourth work project is really trying to help Oxford RF as one of the really interesting, exciting new sensors that is being, or sensor systems that is being deployed onto vehicles. And luckily, having them in the project as a collaborator has meant that we can get very good access to the fundamental understanding of how that sensor is being designed. And therefore, we're not doing a reverse engineering approach to matching performance curves of something, a black box we've modeled. Being able to really understand how, as we say, the electronics are working, the philosophy of transmission and receipt, and then the data packages that are needed to be processed through their own perception systems is so important. Ourselves at RF Pro, we went through that process with Sony, looking at how to integrate their IMX chips into our simulation. And it's fantastic that we're seeing the same appetite from the sensor manufacturers across the industry to come in, not openly telling the world every single detail, but coming and working with us as technical partners to try and make physical copies. I mean, they're virtual copies, but physics-based copies of their electronics. And this is something that I've seen embraced in the imager industry now in the past few years, and it's a massive thing we need to keep pushing into the LiDAR industry and the radar industry to say you cannot bury your head in the sand. And having Oxford RF come onto our project and work with us is a real good sign. And we will be actively trying to get other players in this market to come and do the same thing. So very quickly, just a few fun images really to say about the testing. Mike and his team at Claytex had a wonderful challenge of being up in Scotland for 3 months over the winter, building a weatherproof box, feeding that and leaving that running 24 hours a day for 3 months with a weather station, and having fixed targets. So what we've built up now is a wonderful array of data with lots of different clear days, rainy days, foggy days, and specifically snow. One of the most difficult things in the UK to try and get hold of sometimes. But building up this full array of different weather conditions that these sensors having to perform in to allow us now to move forward and correlate our simulations against them. Then, more controlled, we have our partners at the Catapult and at the MPL and WMG as well that are thinking about how do we test things in laboratories. So not just the weather outside, but the materials that things are reflecting off, and how do we get the best measurement data out of those, both in terms of LiDAR reflectivities and as well as radar. And how is radar then being reflected not just off the human, but the clothes on top of the human? And what's the differences between me wearing this jacket and me not wearing this jacket? Am I safe for one or the other? I want to be the same in both. And our key challenge is really understanding some of the very subtle differences that might exist between different types of clothing on top of us so that we can simulate that and really help people to develop tests and all of those far-reaching tests that we've just talked about, heard about before. Simulation improvements, as we say, touched on this before. We're really looking ourselves at the materials and the weather conditions and the novel sensor development. So operating with Oxford RF. So that was a very, very brief overview, and I appreciate I've skimmed through quite a lot of that today. There's a number of us here from the project. Mike and the team from Claytex are here. Alan from Syslec is here. Ourselves from RF Pro. I've seen Oxford RF themselves have a booth. There may be other people here as well, so sorry if I've missed you. Mike Dempsey is leading the project as project lead. So if anybody would like to talk to us about getting involved, we do have a steering committee. And that really is about bringing you as people in the industry into our project, giving us guidance on what the most critical things you think we should be testing next, and feeding back to you how far we've got to be challenged on this. It isn't just a collaboration as us as organisations. It's open really for everybody to come and try and join us, because it is, as we've heard before, one of the big grand challenges we have. So thank you very much.